Hello, welcome to Fundamentals of Acoustics. Today is the 5th day of the current week, and what we will discuss today is a continuation of what we were discussing in the last class, which is wave propagation in closed tubes. So, what we had shown through mathematics is that in a closed tube, the expression for pressure. So, before we write the expression for pressure, it is important to understand the topology of the tube. So, x equals 0 at the closed end, my positive x axis is in this direction, the length of the tube is L. So, here at the other end x is equal to minus L, and there is a piston here at x is equal to minus L, and because of this pistonic motion, P at minus L T equals P1 cosine omega t plus some phase phi. So, with this understanding, we had developed expressions for pressure and velocity, and the expression for pressure was P1 divided by cosine omega L over C, cosine of omega x over C, cosine of omega t plus phi. And velocity function is defined as P1 divided by Z naught cosine omega L over C sine of omega x over C sine of omega t plus phi. So, these are the two equations which we have developed. Now, what we plan to discuss today is the physical meaning of these two expressions. So, the first thing I would like to say is that this term in green is called the envelope for the pressure. So, this is pressure envelope. And why is it? We will talk about it. Similarly, this term in red is velocity envelope. So, we have a pressure envelope and we have a velocity envelope. And what we will do today is we are going to right now plot it. So, this is the location x is equal to 0. Okay. So, on the vertical axis this is 0, and I will make some graduation points with the hope that using these I will be able to draw a better figure. So, first we are going to draw the pressure envelope, okay. And what we see is that the value of this pressure, the term in the green box, is P1 over cosine omega L over C at x is equal to 0. At x is equal to 0, it is cosine omega L P1 divided by cosine omega L over C, and the value of the pressure envelope for velocity is 0 at x is equal to 0. So, first we will draw the velocity envelope. So, velocity envelope is 0 at this location, and when omega x over c becomes 90 degrees or minus 90 degrees, it becomes maximum. Okay. So, it maximizes at these locations. So, my curve is going to look like this. So, this is my velocity envelope. And this value is P1 divided by Z naught cosine omega L over C. Now, on the same graph, I am also going to draw the pressure envelope. So, pressure is going to be maximum where velocity is going to be minimum, because pressure is the pressure envelope has a cosine omega x over c term, and the velocity envelope has a sine omega x over c term. So, the pressure envelope is going to be minimum here where velocity maximizes, velocity envelope maximizes, and it is going to be maximum here, and let us say the maximum of this is so, the green dotted line is the bound within which this pressure envelope is going to fluctuate. So, these are the points of its extrema. Okay. So, we will draw this. So, this may not be the greatest graph, but it is important that you get the idea. Okay. So, this green curve is the pressure envelope. Pressure envelope. Now, let us try to understand what these graphs mean. So, let us just look at the green curve only for starters. So, this term cosine omega t plus phi. Now, time is changing and time goes from 0 to whatever number it can go up to. So, the value of this cosine term, will fluctuate anywhere between plus 1 and minus 1, right. So, for all positions, cosine of omega t plus phi moves between +1 and -1 regardless of the position, because time is changing, right. So, it can move between +1 and -1, but the value of pressure envelope for a specific location x, the value of pressure envelope at a specific location x oscillates, it oscillates between plus and minus of P1 divided by cosine omega L over C times cosine omega x over C, and as shown by green curve, as shown by the green curve. Okay. So, this term green curve, this term in the box for at a given location, So, consider this location A. At this location, the pressure envelope fluctuates between these two positions, these two values in this range, okay. And cosine omega t at this location at point A, it fluctuates between +1 and -1, and the overall pressure is the multiple of the term in the green box and the term in the purple circle, right. So, the overall pressure fluctuates between A and A prime corresponding to location A. Okay. Now, look at another point B. Let us look at point B. Here the value in green box, it fluctuates between its maximum and minimum possible value, and cosine omega t fluctuates from +1 to -1, because time is just so it fluctuates. So, the overall pressure fluctuation at B is larger than the overall pressure fluctuation between A and A prime. So, overall fluctuation of pressure between B and B at location B is larger than the overall fluctuation at location A, and at some locations this pressure fluctuation is as low as 0 at these nodes, right, and at other locations it is maximum. Okay. So, this is what we see for pressure. The same thing we see for velocity envelope also. It is just that, so once again in this case the velocity is a multiple of the velocity envelope times sin omega t plus phi. Sin omega t plus phi oscillates between +1 and -1 regardless of the position, right. It depends only on time. So, as time changes it just fluctuates between +1 and -1, but the velocity envelope, let us look at another some point, let us look at point C. This is point C. So, corresponding to point C, it fluctuates between these two limits, this is point C. So, velocity envelope also fluctuates, and the amount of fluctuation at each location is changing from one place to other place. So, this is very important to understand, and this is, so the other thing is that this amount is P1 divided by cosine omega L over C, right. This is the amplitude. Now, I have drawn this graph in such a way that the vertical axis is having two different units. There is one system of units for pressure which is in pascals, and another system of units for velocity which is in meters per second. So, just the fact that visually it looks that the amplitude of pressure is more compared to that of velocity does not mean it is in reality more, it is that they are just having different scales. Okay. So, that is important to understand. So, but the point is that the fluctuation of pressure is not, the range of fluctuation of pressure is not same at all locations. It is minima at some location, it maximizes at some location and intermediate at other locations, and the same is true for the same is true for velocity also. So, these type of velocity and pressure patterns are known as standing waves. Okay. And the reason they are known as standing waves is that when you look at these waves or if you take somehow a snapshot of if you suppose you have a rope for instance, and you are vibrating this rope up and down, then the rope appears like this, right. So, the wave does not appear to travel in this case, rather it appears that that kind of a wave is standing, and that perception is there because there is interference of the forward travelling wave which we had seen, and there is a reflected wave. There is forward travelling wave and a reflected wave, and both of these waves interfere in such a way that we get this type of a standing pattern. So, that is why these waves are known as standing waves. The other thing to note is that maxima of pressure envelope coincides with minima of velocity envelope. And vice versa. So, this is important to understand. Pressure of velocity envelope maxima of pressure envelope coincides with minima of velocity envelope. So, wherever you have the maxima of pressure, you will have minima of velocity. And the physical reason for this kind of a phenomena is that at these locations where pressure is maximum, velocity is minimum because the total amount of energy in the system is same. So, wherever you have maximum of potential energy, kinetic energy is going to be minimum, and so on and so forth. So, this is another important aspect to understand. Now, the last thing I would like to do is contrast these type of standing waves with travelling waves. So, we will compare with travelling waves. Okay. So, in the last or the class before that, we had, so what we are going to do here is we are going to relook at this tube which was infinitely long and it was excited at x is equal to 0 through a piston, and such that the pressure here P at 0 t we had defined was 42 cosine 2 t plus pi over 6. Now, the solution for this was P of x t. We had calculated this solution, we had developed this solution is equal to 42 cosine 2 t minus x by c plus pi over 6. Now, this was a travelling wave. So, when we look at this, the amplitude of P of x t at some location x is equal to x 1. What is the amplitude? So, it will be what? It will be for the amplitude of 42 cosine 2 t minus x 1 over c plus pi over 6, right, whatever is the amplitude. And what is the amplitude of that? Now, t is changing from 0 to infinity, and for some t this entire term in the bracket will either be 0 or pi or 2 pi or something. So, regardless of the position of x, the amplitude of the wave is same, and it remains same, which will be 42. So, amplitude of p x t at x is equal to x 1, which is any location in the tube, is 42, and it does not change with position x. So, this is a very fundamental difference. So, in travelling waves the amplitude is constant as x changes. In standing waves the amplitude of the vibration or of the oscillation, it changes from point to point. Okay. So, this is the other thing I wanted to cover. I will now talk about a couple of more things. So, now that we have discussed this, I will introduce 2-3 new terms and close the discussion for today. So, what we have seen is that we have developed expressions for pressure and we have developed expressions for velocity. So, now I define a new term, it is impedance. Okay. And there are several types of impedances. The first one is specific acoustic impedance. And I define it as Z, and please note it changes with position and it changes with frequency. And how do I define it? I call it as the ratio of complex amplitude of pressure wave and complex amplitude of velocity wave. Okay. So, please note this is the ratio of complex amplitudes, it is not the real part. So, what is the complex amplitude of pressure wave for the standing wave which we had discussed? Okay. So, let us look at these. So, this is the relation for complex pressure. So, to find this ratio we have to look at complex pressure relation and complex velocity relation. This term is the complex amplitude for the pressure wave. Time is out, and actually in this phi should also be in it. Okay. And this term is the complex amplitude for velocity. So, when I E j phi should be inside this thing, but when I take the ratios E j phi goes away and I get ultimately specific acoustic impedance. So, this specific acoustic impedance is a function of x, which is position. So, it changes from one point to other, and it is also a function of frequency or complex frequency. So, this will be a complex function, and I can also express this complex function as a function with real part. So, I call it r, which depends on x and s, and a function with n which has a imaginary part which also depends on x and s. So, this x is known as specific acoustic reactance, and K is another function, and it is specific acoustic reactance. So, that is my specific acoustic impedance. So, this Z, what does it depend on? It depends on the entire system, the boundary conditions, the position, the frequency, all of those things. But then there is another impedance which we had discussed earlier, and it is known as characteristic impedance. Okay. And this is equal to Z naught, and this is defined as the ratio of P plus divided by the ratio of U plus, their complex, their magnitudes. Okay. So, the numerator is a number, the denominator is a pure number, and when we do the calculation it works out to be rho naught C. Okay. So, this does not depend on the system, it only depends on medium. And its value is equal to 415 pascals second per meter for air at 20 degrees C, and it is equal to 1.48 into 10 to the power of 6 pascals second per meter for water at 20 degrees C. So, it is important to understand these two impedances, specific acoustic impedance which changes from one place to other, and it depends on the overall system, and characteristic impedance which is the ratio of complex pressure amplitude and complex velocity amplitude, and that is just rho naught C. So, with this we conclude the discussion for today, and we will meet tomorrow, and in tomorrow's lecture we will develop the relation for open tubes. So, thank you, and we will meet tomorrow. Bye.